Hurricanes are one of weather's most devastating phenomena. Each successive year, they grow in strength and wreak more havoc on communities, cities, and even entire nations. Mapping and modeling hurricanes, determining where they are going and how strong they will be, is an increasingly important area of meteorology and can potentially help these endangered communities. Two key parts of hurricane modeling and mapping derive directly from Calc 3: parametric equations and vector fields. But what are these models, and what specific roles do these Calc 3 concepts play?
Parametric equations are one key method of mapping and modeling hurricanes. With all of the recorded hurricane data we have, we can develop complicated parametric equations that model and predict the paths of hurricanes. The 1980 Holland model, for example, is the basis for many current models that can be seen here on the left, while a more modern variation of the model can be seen on the right. These models offer an efficient and cost-effective way to track hurricanes and potentially help communities that could suffer from the storms. So using velocity functions, v r of theta, the models determine velocity based on distance from the hurricanes and angle. Both models utilize extremely complicated parametric equations along with other math beyond the scope of our course, but we can develop simplified parametric models too.
For our parametric model, we begin by looking at the motion of the storm center, or where the hurricane will go, and then create a map of wind velocity. We need to consider the circular motion of the center, which exists because of the interaction between the lower and upper air systems, as well as the drift of which general direction it is heading. So we begin with our equation for circular motion. Here, r is the distance that the hurricane is traveling, and theta is the angular position of the storm center.
We can define r to be whatever distance we want, so we'll call r to be 480 miles. From here, we want to put our equations in terms of time because we are trying to track the motion of the hurricane over time. Also in this model, we have defined our linear velocity of our hurricane center to be 10 miles per hour for simplicity. Next, we can use this equation relating the circumference to velocity to find the period of the motion. Now we know that t equals 96 pi seconds when one period is complete, or when theta equals 2 pi, so we can say that theta equals t over 48, and we get the following equations. Next, we need to account for the radial decay. The radius of the hurricane shrinks over time, so we add in this decay term of 8t. Now our storm is spiraling inwards at a rate of 8 miles per hour. Finally, we must account for the drift of our hurricane. Let's say that it is moving 30 miles per hour at an angle theta equals 30 degrees. We can define the following linear velocities in the x and y direction, and we'll get our final equations of motion. This is one simplified way in which we can model the motion of a hurricane center using only tools from Calc 3.
We can also model hurricane wind velocities in relation to the hurricane center using vector fields. A vector field assigns a vector to each point in a plane or space, showing a magnitude and direction at every location. We can apply these vectors to hurricanes to represent both wind speed and direction of wind flow relative to the eye of the hurricane. For a general example of a vector field, consider the vector field equation f of xy equals x over 2i hat plus y over 2j hat. This function assigns a vector to each point xy, where the components x over 2i hat and y over 2j hat determine the wind's horizontal and vertical directions and magnitudes. The table shows several points and their corresponding vectors. When these vectors are plotted, the resulting graph displays vectors that point outward from the origin, with lengths increasing as the distance from the center increases. This represents a simple model of a general vector field. Vector fields modeling hurricanes will display different, more complex properties. For example, these vector fields model wind speeds and directions for Hurricane Katrina. We can see the magnitudes of the vectors increasing further from the center of the hurricane, and the vectors all point in the counterclockwise direction.
Hurricanes are complicated phenomena. Even if we can't exactly predict their movement, having a sense where a hurricane is going and how much destruction it will cause based on its wind speed allows us to better prepare for them and aid those who will be affected. Using tools from Calc 3, we can better understand the quantitative and mathematical processes involved in developing these models. Thank you for watching.